In this demonstration, we are going to try and embed color in 3 different spaces. The first space would be the RGB, red, green, blue space, and this is the representation most commonly used in computer displays. This is a helper class that I wrote. For example, this is the representation for the green color and the orange color. Green is relatively easy, 0 on the red quantity. Actually, this is 128. We can even go greener. Oh, that's very green. Anyway, and 0 on the blue dimension. Orange is mostly red, somewhat green, and no blue. So this is the RGB representation. RGB is the most commonly used in computer displays, but it is not the most obvious one. People tend to argue what is the most natural representation, and there are 2 contenders. One of them is the HSV, hue saturation value. This is essentially the math required to transform an RGB representation to an HSV representation. And for example, these are the HSV values for green and orange. A bit harder to decipher and understand what does each value mean, but as we can see, the values are different. One thing that is worth to mention is that the distances between those 2 colors change. So in the RGB representation, I denoted the distance with the @ sign. So the distance between green and orange is 1, give or take. And in the HSV representation, they are closer. So approximately a half, which is cool. Next is the LAB representation, which is considered to be by photographers the most natural one, and it's supposed to be relatively linear. Let's have a look how those coordinates look. The LAB representation for green and orange are those numbers. Note that LAB coordinates can be negative, and the distance between green and orange is even closer, 0.4. Okay, now this is the first step of understanding embedding, but I think it's much more easier to understand when we look at the closest neighbors. So these are 20 common colors that I scraped out of a website, and those are HTML standards. So anytime you type red in HTML, this is the RGB representation. Cool. So let's have a look how those colors look like. Red, green, blue, etc. And we can create our own common color. And let's try to have a look, given a query, for example, this color with these pretty random values, and who are its closest neighbors. So the 3 closest neighbors to this pinkish query yellow are apparently this gray color, right? Gray, brown, and silver. Now this is true only in the RGB representation. Let's try and change the embedding to a different function, for example, the HSV. And now we see that the results change pretty dramatically. The closest neighbor is actually some sort of light blue. Not that sure that it's better, right? So we can get some sort of understanding about the HSV representation. Let's try the LAB. Okay, so the LAB looks better than the HSV, but probably worse than the RGB. Let's try a different example, choosing numbers at random here. Okay, so our query vector is green. Within the LAB embedding space, the closest neighbor is pink and purple, magenta, which is weird. Let's see the HSV embedding. That looks better. I guess that yellow is closer to green than pink. And in the RGB space, cool. So the RGB seem to make the most sense. Let's do one last example. So this color is pretty gray. It's closest to gray, which makes sense. Then teal and then purple. Okay, this is the RGB representation. Let's have a look at the HSV. HSV seem to prefer yellow colors for some reason. And the LAB. LAB seem to be very diverse but irrelevant here. Essentially what we did is that we experimented with three different embedding functions, the HSV, RGB, and LAB, none of which had been actually trained to optimize something. So those are just random representations. And we see that the RGB seemed to yield the best result for the examples that we tested. I can't say for certain that it's always the case, but at least we can see that the embedding function is really crucial for recommendation and search. Those are completely different results. Typically, we actually learn this representation with some objective function, and usually the embedding space have a way higher dimensionality. For example, OpenAI have, I guess, 1500 and even more, depending on the size of the model. So with higher and higher cardinality, it's harder to reason about what does each coordinate mean, unlike the RGB representations or hue saturation values that we can actually try and understand what does each coordinate mean. Here we only need to look at the closest neighbors and try to make sense, if that makes sense or not. I think that the trickiest part with embeddings is to understand how to measure them, how to quantify whether those embeddings are good or not. Thank you. I hope it makes understanding embedding a bit clearer.